we'll start it today. We'll finish it by Friday. In fact, I think Friday might be a quick day for us because it depends on how much we get done today. That's all you need for your homework. It involves estimating the value of the difference in two means. And we keep kind of going around in little circles where we return to things and kind of have a different look at them. And so this is very similar to, remember when we found confidence intervals for the difference in two proportions? Remember we did those kind of questions? This is very similar to it, but it's doing with means. So I'm going to start off with an example. So you're going to have two populations, and the first population in this case is going to be American males, adult males, and the second population is going to be adult females. And we believe that males are on average heavier than females, but we'd like to see if we could prove it, right? We want to do an experiment based on collecting information and deciding, is there evidence to prove that the typical average male will be heavier than the typical average female? Seems reasonable if it's true. So we collect a sample, we'll call this one X1, and it was 200 pounds, and there were 100 people in my sample, and that the standard deviation was 15. So I went out and got a nice random sample of 100 males, and I weighed them, and their average weight was 200 pounds, and the standard deviation of these numbers was 15 pounds. And then you go and you collect another sample, but this time it's females, and their average weight is 170. And this was a sample of 200 of them, and the standard deviation was 25. Now, if you just look at the raw data, that's these numbers here, you could probably say with a fair amount of accuracy that it looks like males are typically heavier than females. You agree that the average male is 200 and their average female was 170. But we know from experience that samples vary. Couldn't this just be an unlucky sample where we got a lot of heavy males and a lot of light females, and that's why the averages are so different? Could happen. So what we have to do to get a more precise proof is we collect, or we create, I should say, a thing called a confidence interval. And the typical ones are 90, 95, and 99. Isn't that very familiar? That's the same confidence intervals you do for all sorts of other things. So we are going to do the same thing here. So first thing I'm going to do is calculate the difference in means, because we're going to estimate the difference in values. So it's 200 take away 170, and that's positive 30. This guy here, X1 minus X2, is going to be called the statistic in some of your questions. So you're going to do WebAssign questions, and they're going to say to you, what is the statistic, right? And you're going to have a story just like I have, and you're going to say, it's 30, right? So the statistic is the difference between the first group's mean take away the second group's mean group. In this case, it's 30. And then we're going to get a thing called the standard error. And it's going to be called the standard error in WebAssign. And the standard error for the difference between the two populations. And it has a formula, which I don't know if I've shown you yet. So here goes. Have you seen that guy before? Or is that brand new? Right. If I cover this guy up, isn't that the same as S over the square root of n? That one you have seen, right? So you can imagine it's like P1 hat, P2 hat. Remember the P1, P2 thing that you did with proportions? Isn't this kind of similar in the, you know, one guy plus the other guy, right? So you're essentially finding a way to combine the data from these two standard deviations along with how big the samples were. So in this particular case, the standard error is going to be 15 squared divided by 100 plus 25 squared divided by 200. So I'm going to go to my calculator here and let it do the hard work. So 15 squared divided by 100 plus 25 squared divided by 200. And the answer I get is 2.32, at least to 2 decimal places, right? And maybe you have to do it to 4 or to 3, whatever it tells you in the web assign you do it. I'm just going to do it to 2 because I want it to be 2. And this is called the standard error of x1 take away x2. Now, in my story, I forgot to mention what kind of confidence interval I'm going to create. And I'm going to create a 95% confidence interval. So that's how I'm going to find out if there's evidence. And in particular, for this first version, we're going to find a 95% confidence interval, but we're going to use what's called the empirical rule. The empirical rule is the same thing as the 68, 95, 99.7 rule. Remember that? I like that name better, but that's the empirical rule. Now, if you're going to do that, the 95% confidence interval using the empirical rule, it's going to be x1 bar take away x2 bar, right? The difference, in this case 30, plus or minus a certain number, right, of standard errors. How many standard errors do you get with a 95%? We all comfortable with that? It's the same number that you do when it was proportions. So it's 30 plus or minus 2 times 2.32. So that's going to be 30 plus or minus 4.64. And if you take that away, you get 25.36. And if you add it, you get 34.64. Are we comfortable about how we created this interval? Have you done enough different flavors of that? Yeah, okay. A new formula for standard error, but apart from that, most of it's the same, right? If we did the P1 hat take away P2 hat, wouldn't it look almost identical to this? Right. So it's similar, maybe not exactly the same, but it's similar. Now, let's finish with the conclusion. Would you agree that every single number in this interval is positive? And when the interval is positive, doesn't that mean that the males are bigger than the females? If all the numbers in the interval are positive, doesn't that make x1 bigger than x2? Great. So what we can say here is that we have proof that the average weight of males is greater than the average weight of a female. Now, I think that's reasonable. I think the numbers are just made up, but I'm pretty sure that there is good data. I'm certain I've read it, where adult males are typically heavier than adult females, right? Probably not as much as that, but they are heavier. But in the animal kingdom, that's not always true. Isn't there some species of animals where the females are actually heavier than the males? And aren't there other species of animals where there's really no difference? The males and females are about the same weight, right? So imagine a totally different story and it's not males and females, humans, but males and females, tigers or something else, right? If I got an interval that was negative 11.7 to negative 8.5, right? In other words, all the numbers in the interval were negative. What would that tell me this time?
The second number is bigger than the first.
Right, and another way of saying that, and you're quite right, is that the average weight of the males in this species is less than the average weight of the females, which is exactly what you said, but we tend to phrase it 1 compared to 2, right? So the first thing is bigger than the second, the first thing is less than the second, right, for consistency. Now, in a different world, in a different species, you get negative 1.7 and positive 3.2. Now, in that interval, just like in the proportion ones, right, you get some negative numbers and you get some positive numbers. How do we interpret that confidence interval?
Not enough data?
Definitely true. I would phrase it maybe a little bit differently, but what you said is true. I would say not enough evidence. Instead of not enough data, but I guess maybe I'm quibbling of it, to prove there's a difference, right? If ever you get an interval and it's got positive and negative numbers in it, and you're comparing two groups, right? The difference between two groups. If there's a positive and a negative number in it, that essentially says there's not enough evidence, right? So if we had done it with the males and females up here, we would have only been able to say, there's not enough evidence here to tell if males and females are different in weight. I can't tell you one's bigger than the other or less, could be either. And the argument for why that's true is, isn't 0 in that interval, which means they're identical in weight, but aren't there some positive ones, which means the guys are heavier, but isn't there some negative numbers, which means the females, the girls, are heavier, right? Whatever way you want to phrase it. And I just remembered something that I forgot to tell you. See this number 2 that we used here? He is now got a name. He's called a multiplier. So can you imagine you might get a question just like this story, and they said, what is statistic? You'd say 30. What is the standard error? You should say 2.32. And then they'll say, what is the multiplier? And you'll think, what the heck is a multiplier? Well, you now realize it's that number there. Right, so 2 is the multiplier. At least for this story. Are we good with this process? You feel comfortable with it? Right. So what we're going to do now is say that process works fine. But when you do the empirical rule, it's really an estimate. I know all of them are estimates, but it's just a kind of so-so estimate. Wouldn't it be better if we could come up with an even more accurate estimate for the area, right? The interval, right? Because accurate is important, right? If we can get a much more accurate answer, then that would be true. The empirical rule has got contained inside it some assumptions that may not be true. You can only really do the empirical rule if the samples are big enough, which I guess in this case they are, but the distribution should be nice and normal. And it's not guaranteed, isn't it, that I know we're very flexible about how normal is, but couldn't it be that it's quite skewed to the left or skewed to the right and you wouldn't know? And you could come up with bad answers. So what we want to do then is, or what they decided to do is create a much more accurate way of estimating a confidence interval. And it doesn't care if the samples are tiny. So you could do this estimate with 10 people and 5 people. That's good. And it doesn't care if it's skewed to the right, like horribly skewed to the left or right. This method still copes with it, right? So it's a pretty powerful method, and it uses a guy called the student t distribution. So basically, unless you see the words empirical rule being used, you're going to assume that we're going to do it with the t distribution. Now, the formula for calculating it is x1 bar take away x2 bar, right? Well, where's my formula? Right. Same formula, plus or minus a funny guy called t star, a funny guy called, by the way, the multiplier, times the standard error of x1 take away x2 bar. So it looks like the only thing you need to change, remarkably, is the number that you use for the multiplier. So instead of using the empirical rule, which is a kind of rough rule of thumb, oh, it's about 2-ish, right? We just use 2. We're going to use a much more efficient and accurate guy called t star. And now I have to show you how to come up with T star. And you have to use salt, and you have to introduce some things we haven't really spent a lot of time in. First thing you need to know, there are only two things you need to know. One of them is degrees of freedom. Very often called DF in textbooks. And the degrees of freedom is a number. It's the number in the first sample plus the number in the second sample, take away 1. In some textbooks, it's the number in the first one plus the number in the second, take away 2. Yeah, pick your poison. Let's just stick to 1 and call it good. So in my story here, there's 100 of these, and there's 200 of these, and you take away 1. So what we've got is 299. So we need to know degrees of freedom. Right? And we also need to know what confidence interval percentage are we looking for. So in this story here, it was 95%, right? So let's find out who the multiplier is. I call magic number. And I'm now going to go over and show you, hopefully, how to do that. And you can't do it really without salt. So this little bit does need salt. You can't avoid it. But the rest of the calculations are fine. Are you looking at something that looks like question 8 in front of you? Right. I'm just using this to get a salt button. And I'll bring it over here. Now, the guy that you want to use is distribution calculators. You see that guy there? Make sure you're using that one. Let me shrink this up a little bit more. Right. Make sure you're using that one. Don't use inferential statistics. It looks very similar. Use distribution calculator. Now, click on this and pick T distribution. Right. So pick on the top one, T distribution. In the box called degrees of freedom, put the number that I just calculated. In this case, 299. So far, so good. Now, scroll down to, scroll over here, and you see the one that says between. Click on the between button. And then go here and put in your 95. So let me show you all the pieces again. T distribution, degrees of freedom 299. Make sure that you're always on this between button. And then make that number at the bottom 0.95 because I want a 95%. Now the magic T number is that guy there. And you see roughly it's 1.97. Do you see how I got that guy? 1.97, it's here. So let's return and look at finishing off our question. Now, would you look at the difference? Would you agree that there's not a heck of a lot of difference between 2 and 1.97? I mean, it's just minor, but this is considered much more accurate. So let's go and finish the story then. So x1 bar minus x2 bar is going to be 2.32 plus or minus the multiplier, which is 1.97, times the standard error, which, there I go and do it. The standard error is 2.32. This number here is 30, right? 30 plus or minus multiplier, standard error. So it's 30 plus or minus those two guys. So 1.97 times 2.32. 1.97 times 2.32. And I'm just going to call that 4.6. So it's going to be 25.4 to 34.6. And that is us found our 95% confidence interval. Not that different from the one that we had, right? So let me pick one as my next story, where there would be a lot of difference if you use 2 instead, or whatever you might choose. So let's have a story about people from Alaska and people from Texas. And you don't know this because I'm making this up, but I collected some pretend data, right? Pretend it's not pretend data, and I found out that the average number of units of alcohol an Alaskan drinks in a week was 17, and for a Texan, it was only 12. And a unit of alcohol is like half a pint of beer, or a bottle of beer, I think, is a unit of alcohol. So Alaskans are a bunch of drunks, right? So if anybody's from Alaska, I apologize. But we'll pretend that this is data. It's true. It's totally made up, by the way. The standard deviation here is 5, and the standard deviation here is 1. Would you agree that there's a lot of variation in Alaska? Right? So there could well be a lot of people drinking even more than this, but an awful lot of people drinking a lot less than this. On the other hand, aren't Texans pretty consistent? They all drink about the same, right? Small standard deviation. This is the killer. I only asked 10 of these guys and 15 of those guys. Would you agree those samples are so tiny, you shouldn't be doing empirical rule on it? But you are allowed to do the t-distribution on it, which is kind of cool, right? So let's get our thing that's called the statistic. Let's get the numbers we need. And that's going to be x1 bar, take away x2. In this case, it's 5. And let's get the standard error. In this case, it's going to be 5 squared over 10 plus 1 squared over 15. And square root 25 divided by 10 plus 1 divided by 15. And the answer is 1.6, roughly. Right, before I continue with this, do you think a difference of 5 is a big enough difference based on the fact that these samples are very small to still be able to prove that Alaskans drink more than Texans? Kind of hard to tell. You got a gut feeling? I'll put somebody in a spot. Barbara, what comes into your head? It doesn't need to be right because I don't know either. What do you think? There's enough evidence that Alaskans drink more than Texans?
No, I don't think you have enough evidence because it's too small.
Sample sizes are just too small.
Mm-hmm.
Seems reasonable. Let's find out. Now, there's only one guy left. I'm going to call it T star because that's what it's typically called, right? Now, to get T star, don't we know, or we need to know degrees of freedom? And what confidence interval should we do? You can pick any number you like, 90, 92, 95, 99. What do you want?
Let's do 96.
Okay, just because we want to, 96. It's not a standard number, but nothing wrong with that, right? 96 is as good as any. So degrees of freedom, remember what it was. It's the first guy plus the second guy, take away 1. So in this question, they're going to be a degrees of freedom of 24. Right. So far, so good? Right. Let's nip over and see what salt does. I don't think I'm on that yet. When you look at this guy here, it's the same picture as I had before, but we'll go through it as if it was totally fresh. You hit distribution, bump. You make sure it's T distributions, right, that one. You click on degrees of freedom, in this case, it's 24. You go down here and you make it a 96% because that's what you wanted. And you see that this time the number's what? 2.1715. Let's call that 2.2. That seems reasonable, rounded off value. And let's stop and see what the rest of the question looks like. So we have the multiplier. We know the standard error, and we know the statistic. So a 96% confidence interval. If no one mentions what it is, we'll assume that that always means t-distribution, right? If they wanted empirical, they really have to say it. So if they don't mention it, you're going to assume it's this guy. And so what we're going to go and do next is x1 bar take away x2 bar, the statistic, plus or minus the multiplier times the standard error. And this guy happens to be 5. The multiplier is 2.2, and the standard error is 1.6. And we get 5 plus or minus 2.2 times 1.6. And the answer we got is roughly 3.52. And if we take it away, and I'm surprised as well, it's 1.48. And if we add it, it's 8.52. And that's interesting, Barbara, that it's still positive in both cases, right? Everything is positive. What does that tell us then? What have we got evidence to show now that all the numbers in the difference interval are positive numbers?
That X1's greater than X2.
And in the context of this story, the average Alaskan drinks more. Sorry, get that wrong way. Yeah, it's the right way around. The average Alaskan drinks more than the average Texan. Even although it was a tiny sample. Would you agree 10 and 15 is tiny? Didn't we still get a result that has evidence? Now, you know, like evidence analogy, do you know in a court of law, people get convicted and they didn't do it, right? If this was a court case, wouldn't that person be convicted? i.e. Alaska would be convicted of drinking more than the other people, right? Based on the evidence. But isn't there a 4% chance that an innocent guy's in jail now? Could we be convicting them on the wrong data, right? 96. Isabel, question.
I was just wondering how you got the 2.2 for the T. Just like you probably showed it in SALT, and I must have missed it.
Okay, say it again. I missed the beginning. You kind of died away in your voice.
How did you get the 2.2 for the T?
How did I get the 2.2? Is that what you're asking?
Yes.
Okay, let me talk you through it again. Give me a second to go back to SALT.
I just think I missed it. It's in SALT.
Fine. I'd rather you were sure about it than not. So I have no problems with that. So here we have a t-distribution, right? Degrees of freedom were 24. I got that by adding the 10 people from Alaska plus the 15 from Texas, and then you take away 1, so that's 24. Make sure that's always on the between. And then down here at the bottom, you put the confidence interval you want. So this guy is a 96% confidence interval, right? And on a 96% confidence interval, the magic t-score, right, the magic multiplier score, whatever you call it, is that guy there. And I've rounded him off to 2.2. Okay. And it ended up being a significant answer, right? All the numbers were positive. What would you think would happen if the only thing I changed was a 96, say, to a 99? What do you think would happen to the multiplier? Would they get bigger? Would they get smaller, or would they be about the same? Going up? Bigger. Yeah. So right now it's 2.17. If I made it a 99, do you see it's already climbed to 2.79? You see that? 2.79. Right. I'm going to use that as the next version. We won't need to do too much extra, thankfully, because all the numbers are going to stay the same, except for the multiplier. So that was a 96. If you did a 99%, it would be that guy who's still 5. The multiplier has now become 2.79. I'm calling that 2.8 times 1.6. And now you've got 5 plus or minus 2.8 times 1.6. And now it's 4.48, which is 0.52 to 9.48. Would you agree that the intervals are still positive? But aren't they getting darn close to meeting, you know, the overlap? So this would still be proof that the average Alaskan drinks more than an average Texan. So I'm going to do one more. I'm going to do a 99.9%. Right, if you're going to put somebody in jail, would you probably want to be 99.9% sure? Right, you don't want an awful lot of innocent people in jail. So let's say that our justice system would be looking for a 99.7% evidence. I'm now going to go back to that guy. And for the last time, we are going to calculate what the multiplier would be. And if you make this guy 99939s, it now turns into, I've lost the guy, 3.74. You see it there? Okay, so I have 5 plus or minus, call it 3.7, 1.6s. And in this final version of that story, it's 5 plus or minus 3.7 times 1.6, 5.92. And now it's negative 0.92 all the way up to 10.92. And in this case, there's not enough evidence, is there? Because doesn't this interval, we say it contains 0, but I like to think of it as had negative and positives in it, right? Now, we never changed our sample. We never changed the results that came from our sample. Didn't we just change the confidence interval that we were using to base our decision on? 96, they're guilty. 99, close thing, but they're still guilty. By 99, not enough evidence. Now, in a way, doesn't it depend on how comfortable you are at being wrong? Right. If this is people in Alaska and Texans drink, would you agree 95 or 96% would be fine? Okay, I get it wrong 1 in 20 times, but nobody's going to die because of it, right? Some Alaskans are going to be offended by being called, you know, drunks, but apart from that, nobody's going to be that bothered, right? On the other hand, if we are conducting a trial, which is what my next one's going to be, between the effectiveness of 2 different drugs, don't you want to be 99.9% sure when you say the first drug does a better job than the second? Because if you got that wrong, couldn't people die? So this is up to the person who's conducting the experiment, right? I mean, couldn't I do a 90% if I felt like it, you know? But I'd be wrong 1 in 10 times. Are we good? Just going, I don't know if the word is scarily, but it seems to be going, because I can see a lot of faces, reasonably well. You feel we're doing questions that kind of make sense. Right, so I'm going to do one more of these. It's going to be a drug one, and then we're going to look at the homework questions, because you have to deal with how WebAssign asks you the same questions that I've just done, and we have to get comfortable with that. So we have drug 1 and drug 2. And drug 1 is going to be the new drug, and drug 2 is going to be the old drug. And both of these drugs are meant to, I don't know, what can they do? They're meant to reduce your blood pressure, right? So if you take drug 1, you get your blood pressure. You take drug 2, you get your blood pressure, right? We're looking at what the average reduction is. So if you take the new drug, they found out that you managed to reduce their blood pressure by 15. For the old drug, it was 14. The standard deviation was 5, and the standard deviation of the old drug was 3. And the sample size was 200, and the sample size was 300. So you found 500 volunteers who have an issue with their blood pressure, and you're going to split them randomly into a group of 200 and a group of 300. These guys are called the control group, just to, bring back terminology from other sections. And this is called the experimental group. Wouldn't this probably be a double-blind experiment, where the people getting the pill don't know which one they're getting, and the doctors who are measuring their blood pressure and recording it, they don't know either, right? So what we're looking at here is our evidence to show that the new drug is better than the old. Now, when I look at the difference, would you agree that a difference of 1 isn't a lot? But it is a difference. Would you agree it's, for some reason, all my questions seem to be the first guy bigger than the second, but it's not really vital. Would you have a guess that this is probably going to be no evidence situation? Right? But let's find out, because you get surprised, Barbara. I got surprised as well with that last one with the Alaskas, right? With a tiny sample, it still was. If the difference is big enough, won't you be able to prove things are different, even with small samples? Right. So 200, 300. Let's go for it. The statistic, which is what we call this guy, is going to be 15 take away 14, 1. The standard error is going to be the square root of S1 squared over N1 plus S2 squared over N2. In this case, it's going to be 5 squared over 200 plus 3 squared over 300. So the standard error we're looking at here is the square root of 25 divided by 200 plus 9 divided by 300. And I'm going to call that, well, 0.39. Can we just call that 0.4, because it's easy to calculate, right? 39 in a bit, 0.4. I'm happy with that. Put little circles around the guys, so when I go hunting for them, I can find them. Right, only one guy left, the multiplier. So it's going to be N1 plus N2. No, it's not. The degrees of freedom are going to be N1 plus N2 take away 1. So that's 200 and 300 take away 1. That's going to be 499. And I've forgotten what the confidence interval would be. What do you think a confidence interval should be if you're talking about medical drugs in people's lives? Do you think I should do a 90%? 99? 99? We'll settle on that. Okay. So let's suppose in the question they would tell you that. So you don't need to decide what the percentage is. In the questions, they'll tell you it's 99 or whatever it is that they give you. So let's find out who the multiplier is. I'll just nip back to salt and we'll see what we get. T distribution already, gotcha. Degrees of freedom, 499. That's a pretty decent sample size actually. And this fella here is going to be 99. And so it's 2.5859. So what would that be? 2.59. So I'm going to use 2.59. Are we comfortable how we're getting the multiplier now? Once you see 4 or 5 of them, it becomes second nature. Now let's put the whole package together and see what a 99% confidence interval is going to look like. So it's going to be x1 bar to give x2 bar plus or minus the multiplier times the standard error. That guy is 1. This guy is 2.59 and the standard error is 0.4. So it's 1 plus or minus 2.59 times 0.4 comes out to be 1.036. If you subtract it, you get negative 0.036. I'm trying to do that in my head, and 1.036. Oh, interesting. What conclusion, if any, can I make?
Shouldn't that be 2.036?
Thank you. It should be 2. I was too busy focusing on this guy. What conclusion, if any, can we have from this confidence interval?
You
There's
can't.
not enough evidence to support or
Agreed.
to calculate.
Right. Not enough evidence. I don't have time, but can you pretend that I did a 90% confidence interval? Or actually, I could probably even do a 95% confidence interval, and I might end up with an answer that looks something like this. Can you see if I did a 95%, wouldn't all the numbers be positive, in which case the first guy is actually doing a better job? If I did a 90, I would pretty much guarantee that would happen. I'm not 100% sure it would happen in 95, but I guarantee it would happen in 90. Can you see then that you can come up with different conclusions based on the confidence interval being used? So if you ever see data in a medical field or you see data in any situation and they're using confidence intervals, pay close attention to what number their confidence interval was. Typically in science, we stick to fixed ones. So I know we did a 90-60 day just to show you it could be done. But in a normal science, you do 90s, you do 95s, you do 99s. Rarely, but I have seen them, you do a 99.9. Right? If you see a set of data and somebody said, I used an 85% confidence interval, and now I have proved something. Well, you say to yourself, no, you haven't proved anything. Haven't you adjusted the confidence interval to make this happen? Can you see that there is the opportunity, let's call it that, to adjust the confidence interval to prove what you're trying to prove? Now, it won't prove white is black, right? It won't swap the truth, but can't it at least nudge the truth in a direction that you want it to be? And that is human nature being like it is. Can you see that there's a huge temptation in the scientific world to do that? I mean, can you imagine you spent 6 months of your life collecting data on something, and at the end of that 6 months, this happened? Would you agree there's a strong temptation for you to make this happen? Because
the lowest, kind of confident interval has to be is 90? Like you can't go lower than that?
Definitely never going lower than 90,
Okay.
right? And that's just, everybody would laugh at you if you tried, right? So we all know that one. But you should only live in these four, right? And you have to be aware that some people in scientific situations have a lot of, you can't publish a paper saying, I just spent 6 months doing stuff and my conclusion is I haven't found evidence to prove something. Would you agree I haven't found evidence to prove something is a pretty boring scientific paper? Actually, they don't even get published because you've told me nothing, right? Aren't you likely to get published if you say, I have shown that blah, blah is bigger than other blah, blah, right? Even if I had to tweak my confidence intervals to make that happen. Putting it out there as a thing to be aware of, a risk that can be. And the FDA, the people I like referring back to them, you know, I don't like governments, but I do like the FDA. When they do medical trials, right, they test drugs. They don't say to the pharmaceutical company, I just pick whatever confidence interval you want. We'll look at your data. No, the FDA, I don't know what the number is. I hope the number is at least 99%, right? I would hope they would say that. Like, you got to do a 99% confidence interval. That's the data we want to look at, right? Now, they may have different levels, you know, they might have a 99 for dangerous drugs and maybe a 95 for aspirin drugs, right? You know, things that don't kill you, but, you know, they're not so worried. They might have that. I can't say yes or no to that because I don't know, but it might be true. So let's look at the homework. Let's like figure out where the darn it is. I think I found it. I definitely think I found it. Good grief. I should do the lottery today. I found it on my second click.
The FDA says that they use a 95% confidence interval.
Oh, how do you know that, Eric? Did you just look it up?
Yep, Google.
Google. There you go.
That's according to the
95.
FDA website.
Hey, I was pretty good on my guess, wasn't I?
Expect them to use something better, but you know, drugs.
Well, I don't know where I am. You've talked me right off my game here. I was doing well until you did that. Sugar spicing. Have you noticed how good I am at not swearing? Do you know this is a theory that I have. The reason I don't swear much, and I don't swear too much, I swear at Seahawks games when they drop the ball and get intercepted. So I do swear occasionally. Is that I was brought up, as I said, with 6 sisters and a mum. And can you imagine that you weren't allowed to swear? And so it get knocked out of me pretty quickly. So I think I'm putting that down to feminine upbringing, even though I do like girls. Having lots of females in your life does change parts of your personality and what you do or don't do. And so that's my excuse for why I don't swear much. Oh God, I got to tell you because it's in my brain now. Our dog's passed away, but we had a dog called Mac, who was a Westie, just like Bailey is. And I was taking him out a walk one day, and this is to do with me swearing. So I took him out a walk one day, and he literally snapped his leash and he shot off. And I was panicking because he shot off towards the main road, and I thought he was going to kill himself. So not being that fit and being kind of shocked, I ran after them and I lost my balance and I thumped my knee. I ended up in hospital actually, thumped my knee, and I was lying on the ground. I thought I'd broke my leg. I was in pain, and I was being a sailor. I definitely had a few choice words going on there as I was holding my leg. And my dog that was running away came and he just looked at me thinking like this. He does the head thing. What are you doing? What are you doing? So I can't get up on my leg. I can't walk and nobody's around. And so I grabbed my phone and I thought, I'll phone my wife and tell her, come out. She was in the house, come out of the house and get me, because evidently my swearing didn't have any effect because she didn't know it was me because I don't swear, I guess. So some drunk outside swearing. And so I phone and couldn't get through. And so finally I kind of got up on one leg and literally hopped and occasionally fell down, which wasn't fun. And I got to the house and I opened the door, and my poor wife had to suffer a string of abusive comments connected to, why didn't you pick up bloody phone, and why didn't you do this, and I'm in agony, and call the ambulance, I think I've broken something. And that was one of the few incidents in my life I've ever swore at my wife or swore close to my wife. And it wasn't really her that was swearing, I was just swearing at the pain and the frustration of not being found. Thought I'd share that for no particular reason, except it was in my head. So let's look. Are we looking at chapter 11, guys? After all that, okay. Let's see how these guys can make our life a misery by making even the most
Keys
obvious
on.
mistake. Say again?
The key's on.
Oh God, we hate keys. It does that kind of automatically when I open the darn thing up. Right, key's gone. Good. Let's see how WebAssign can make the obvious less obvious. Okay, first question. Is the mean of a sampling distribution always 0? The assumption is that it is going to be 0, but you have to go through which one of these it is. And the mean of the sampling distribution is 0, because we start off with the assumption that they're equal and we look for evidence to prove they're not. It sounds backwards, but that's how we do it. Now, in situations for which the parameter of interest is the difference between the population means, is it necessary for the two samples to be the same size? No. So one of them is no. Okay, what's this one? Nah, it's boring.
Wait, so which one would have?
Oh, which one? There's something to be approx. Oh, I didn't read on. To be approximately normal. Don't both samples have to be large? They just don't need to be the same. Right. To be normal, don't you have to have, one of the things you have to have is large samples, right? Yeah, that one did catch me. Well, I didn't, I said it was no. But if you want it to be approximately normal, you need to do that. If you want to just use the t distribution, don't you just need them to be different or not? It doesn't matter. Okay, 3, volunteers who have developed a cold within 24 hours were randomized to take either a zinc tablet or a placebo. And they do it every 2 or 3 hours until their cold symptoms were gone. Okay. 25 participants took the zinc and 23 took the placebo. Okay, so I guess what they're measuring here is if you've got the cold, do zinc lozenges actually help you recover quicker? In other words, you get over the cold quicker if you take zinc. You can actually buy them, can't you? If you went to Safeway, you can buy them just on the aisle, right? Don't you also get those other little packages with vitamin C and you put them in water and drink them and all sorts of other things, right? So there's various things out there which are not FDA approved, by the way. Do you know how they get around them not being FDA approved?
They call it a health supplement.
Yeah, they call them supplements, right? So, you know, you can buy big boxes of vitamin C and you don't need to get a doctor's prescription or anything because the FDA don't treat those. I'm pretty sure they've checked that they don't kill you, right? But apart from that, they don't check effectiveness. So what parameter of interest in this situation? Well, the parameter of interest is, isn't it the difference in the times? mu1 minus mu2. And where mu1 is the time for the first guys and mu2 is the time it takes for the second guys. That's the end of that one. What is the sample statistic here?
Wait,
What the
which
sample?
one?
So that would be this top one. Right, the parameter is mu1 take away mu2. The statistic is x1 take away x2. Remember, parameter was p1 take away p2, and statistic was p1 hat take away p2 hat. It's the same kind of information. Now, what is the sample statistic? Is it the sample statistic x1 take away x2 by? Right, and that's that one taken care of. What are the conditions that have to be met for it to be approximately normal? Okay, we did approximately normal kind of yesterday, no, well, Monday in our case. What were the two conditions for something to be normal? Then we'll go figure out which one they are. You need two things.
A large sample size
And, correct, and
and normal shape,
normal
bell
shape.
shape.
Right, so one of these is a bell-shaped and decent-sized data. So I'm trying to scan through them. I'm not good at scanning. Because sample sizes are small, the population symptoms would be lots. Yeah. Okay. Do we know anything in this story? Yeah. As far as I can tell, isn't the samples too small and there's no evidence that it's bell-shaped? So one of these is both reasons. I can't even read that right. Because the sample sizes are small, okay, which they are, the population of times symptoms would last under the, does that, am I reading that funny or does that just read funny?
I think it reads funny.
It does.
It's confusing.
It's very confusing. I think it's computer bad at grammar. One of those guys better be what Barbara says. Since you have 5 guesses, won't you eventually get the right one? So let's not get too caught up on that one. I'm not going to lose any more time over it. Right, here we go. In a research study, volunteers, oh, they got the cold story again. 22 participants, right? Took the zinc. I'll write that down in case I need to do it. 22 participants took the zinc. And if I read on a bit further, 27 of them took the placebo. Okay, got that. Suppose in truth, if everyone in the population took a zinc lozenge, your symptoms would last 3.5 days. Okay. And if you took the other gun, it would last 9 days. What is the mean of the sampling distribution going to be? Isn't it going to be the first guy, which is 3.5, take away the second guy is 9. So that would be negative 5.5. Are you happy with that negative 5.5? Zinc take away placebo. 3.5 take away 9.
They say to use placebo take away zinc in the question.
They didn't. They did, didn't they? Okay. Wouldn't the answer be 5.5? And moral of that story is always read the question, right? What is the standard deviation of the sampling distribution for the difference in sample means, and write your answer to 3 decimal places? So somewhere in here, they should give me the standard deviation. And the standard deviation is where?
2,
Is it?
the bottom.
Oh, okay. Are they both 2? No, one of them is 1.5, agreed, and the other one is 2. Okay, so it's going to
Answer
be,
for A be 3.5, not 5.5.
You wrote 9 minus 5.5
Uh,
instead of 9 minus 3.5, or however it's supposed to be written.
Okay.
Oh, is it written wrong? I was just looking at it. I was like, that's.
The
Yeah, because
calculation.
the answer for
uses-
him is 5.5. It was just written wrong.
There we go. I think I finally got this one right. Isn't having 5 guesses useful? Right, now in the standard deviation here, that's really going to have to return back to the piece of paper. Let's just remind you how to get the standard deviation again. So I got to figure out who X1 is and X2 is. In this case, it's going to be placebo and zinc. Okay, and S1 and S2 then. If I look at the placebo and I look for the standard deviation, which is in here, if I read far enough, the zinc people took 1.5 and the other lot was the 2. And the X bar one was the placebo was 9 days and the X2 was 3.5. Right, there we got all the guys. So if you want to get, and N1 and N2. N1 is the number of people who were in the placebo group. And there were 27 of those. And N2 was 22. So the standard error of the difference between these two is the square root of S1 squared over N1 plus S2 squared over N2. Oh God, time's shooting by. Square root of 2 squared, which is 4, divided by 27, plus 1.5 squared, which is 2.25, divided by 22. And I get the answer, oh, that's a nice number, let's call it 0.5. Okay, so let's return back to how they do the questions in WebAssign. And how many decimal places? 3 decimal places. So how about 0.500? Because that's what it was in my calculator. Now, assuming that all the conditions are met and normal and all that good stuff, find the difference in the sample means of this distribution. This guy here, do you recognize this guy here as the 1, 2, 3 standard deviation picture? Right. Now, 5.5 in the middle and going up in 0.5. So let's find out 5.5 in the middle, going up in 0.5. So would you get it's that one? 5.5, add 0.5, add 0.5, add 0.5, take away 0.5, take away 0.5, take away 0.5. Now, in the study, the sample mean duration of symptoms was 3.5 days and 9.2. Okay, let's read this one. In the example that we just talked about, you got 3.5 and you got 9.2. And that gives us a difference of 5.7. Okay, so the difference is 5.7. Now, if you look at this guy, 5.7 is roughly where my mouse pointer is. Do you agree about that? Would you agree that is well within the range of what you would expect? So, falls just above the mean, right? And its corresponding Z score of, oh, they threw in a Z score. Now, to get the Z score, it's data, take away mean, divided by standard deviation. So let's see what that looks like. Didn't even expect that, but we can handle it. The Z score is the data, take away the mean, divided by standard deviation. Right, in this case, the data was the difference, 5.7. And the mean that we had earlier was 5.5. And the standard deviation is 0.5. And I get 5.7, take away 5.5, all divided by 0.5, and I get a z-score of 0.4. Would you agree a z-score of 0.4 is just typical, nothing interesting? What kind of z-scores are considered outliers, exceptional?
Anything above 1 or below -1?
More than that. The test for outliers. I see some fingers. 3? Yeah, 3 standard deviations. So that is well within tolerance, right? There's nothing to see here, essentially. So if I return back to that
Wait,
question.
where do you find the data again?
The data came, I'll show you it right now. It was in the story. In this case here, the data was the 5.7. So they actually did and they got a number. And I'm comparing that against this as the mean. You see the mean is 5.5.
Yep.
The data was 5.7. And then I divided it by our guy, all good, our standard error. And
Okay.
everything came out pretty good. So we would put in a z-score here of 0.4. And so it is reasonable, right? If we had done that experiment and the z-score was 3.2, wouldn't we say that that was highly unlikely? There's something going on here, something weird. It would be an outlier. Okay, in this question here, it looks like it's pretty much a standard question. So let's see if we can do it pretty quickly then. The mean and standard deviation for the heights of adult males above 70 inches and are about 70 inches and 2 inches for the standard deviation. So for guys, height is 70 and standard deviation is 2.8. For females, it's 65 and 2.3. Are we good so far? Right, so won't this one just be guys, take away girls, and 5? We're happy about that. Now, to get the standard error, wouldn't we do the S1 squared over N1 plus S2 squared over S2 and all that good stuff here? And
You'd type 70 minus 75 instead of minus 65.
what did I do? Oh, good and grief. That's just me hitting the wrong buttons. Right. Yeah, this one is pretty much the same story with, if all the intervals are positive or negative or contain one of each, won't it be one of these answers? Right. So if I go back to that question and see what kind of sample they're doing. Okay, they're just doing it spell shaped. Right. Here's one. Yeah, we've got time. The following data set represents the weight of eggs from a sample of 10. And here are all the numbers. And then they ask us to find that mean, which is a pain in the butt because won't you have to add them all up and divide by 10? Since I don't have time for that, can we pretend that I'm really good at counting and it's 52? It's not 52, but just for argument's sake, it's 52. Now, here we are going to consider 2 samplings. Egg producer 1, mean of 51, standard deviation of 3, 45. 53, 3, and 60. If you take a random sample of 45 of these, the difference, since this is population values,
Is that
is-
Scott? Nice job,
that-
though. Okay.
oh, okay. So we 51.8 try and get this the right way around for a change. 53.8. Oh, good. Nice numbers. Would you agree that these two egg producers aren't producing the same kind of eggs? Isn't the answer that there's a difference of 2 grams, right? So I guess it's a weight of eggs.
Is
Now, if
that
you
a
want-
negative?
You're right, it is. Thank goodness for first negative. Determine the standard deviation. Oh, God in Himmel. I don't have time for this, but won't it be that the square root of that guy squared divided by 45 plus that guy squared divided by 60? And just for argument's sake, can we pretend it's nothing 0.2 so I can put a number there?
Can you just write down like the formula for that?
Sure. I'll have to go to the paper. Oh, the formula for calculating the standard error. When you are doing samples, it's a square
I
root.
don't think we can see.
Oh, you can't see it yet?
No, we just see like a blank white screen.
That's me and hitting weird buttons. There. You got
There
it
you
now?
go.
Right. The standard error, which is what they're asking here, for the difference between these two, is S1 squared over N1 plus S2 squared over N2. And that's the formula that you will use when the data is in the form of samples. If you are actually told the population numbers, the only real difference you do is that you use the standard deviation of the populations. So it's standard deviation squared over n plus standard deviation square of n. So in this story, we are looking at, for the first group, it's 3, so it's 3 squared divided by 45. And for the second group, the standard deviation is also 3. And
Over
it's out to
60.
60. Right. So watch me make another mistake. I don't mean to, but I guess I'm getting old. 9 divided by 45 plus 9 divided by 60. And that comes out to, how many decimals do we want? 3 decimal places. So that would be 0.592. So that would be our standard error. I guess I should call it mu one when we're using populations, but I'm just getting lazy with that one. So that would be 0.52. We already know the difference between the two, which in this case was -2. And that's it. The formula for calculating the difference is just subtract them. And isn't the formula for calculating the standard error, whatever standard deviation they give you squared over n1, plus whatever standard deviation squared they give you over n2. Equivalent. Can you remember doing the proportion ones where sometimes it was p1 hat you used and sometimes it was p, right? They gave you one or they gave you the other. Remember those questions where some stories told you p and some stories told you p hat, right? Same formula, isn't it? And essentially the same information. This is population numbers, but the formulas are identical. I got time for one last one. And, you know, they like doing things their own way, just fine. Each of 63 students in a statistics class used their non-dominant hand to print as many letters of the alphabet in order that they could in 15 seconds. Okay, don't know why you'd want to do it, but they did it. The following output, which is basically what you see here, contains pretty much everything that you need for a 95% confidence interval. So, females and males, 29 females, 34 males. Females 12.3, males 13.5, standard deviations, they even told you that, but I don't really need to know that. The difference between females takeaway males is negative 1.278. If you take this number and subtract that number, will you agree that it is that? You could have calculated it, right? So if you went 12.31, subtract 13.588, you would have got that. And isn't that basically our statistic? Right. Now, what else do you need to know? You got a t-value, you got p-value. There are stuff here you don't need to know. They even tell you degrees of freedom, which is a funny way for them to do it, but that's fine. What was the mean number of letters printed for females? Well, if I go up here, isn't it just that number there? And for males, ones that just matter going to that number there. And the difference is that number there. And the 95% confidence interval, isn't it these two numbers? So from that number to that number. So the difference between males and females is somewhere between negative 3.5 letters or positive 0.964. We'll worry about their sentence. Here's my question instead. Is there evidence to prove that males and females are different? Like males are better or worse than females based on that interval? The difference is between negative 3.5 and positive 0.96.
There's not enough evidence.
It's a not enough evidence one. Would you agree? If all of those numbers were positive, wouldn't that mean guys were better at writing down with the wrong hand? Or if it was negative, girls were better, right? Whatever way you want to phrase it. Now, writing it separate, this interval. This 95% confidence interval. Right? We can estimate that among all students who take introductory to statistics class, I'll have to shrink it to see the whole thing. Okay, I've lost my question. Here it is. Right. With a 95%, that's not the question, but it's my question.
Number 7.
Thank you.
Part B of 7, yeah.
Just changing the size and then it goes and changes everything on me. Here we go. Right. The first choice was we can estimate that among all students who take an introductory statistic class, the difference in numbers of letters printed for female and males is contained within that interval for 95% of students. Nope. Nope. Look at this one then. With 95% confidence, we can estimate that among all students who have an introductory statistic, the difference between them is this one. And that's the one that works. When I do a 95% confidence interval, aren't we saying that the true difference is somewhere in that range and we're 95% confident? Of the 4 sentences, that one makes the most sense. This one here factors in the 25 students. I'm not sure why they did that. Now, if you take this number here, you can draw it on a number line. And I want a negative 3.5 to a positive 9. And from what I can see, would you agree that looks like negative 3.5 and that looks like roughly 0.9? You agree on that one? Right. And go through all the stuff here. Get this finished quick. Refer to all the stuff that happened before on the basis of a 9. Oh, I've already done this question. Then I ask you, is there evidence to prove? And we decided that because there's pluses and negatives, that there's not enough evidence to tell. So now we have to figure out which one of these is it. So let's look at this one. Since the interval is, oh no, that's not the one. This one. Since the interval contains 0, we cannot say that for the population represented by this sample, whether on average there is a difference in the number. That's the one. Would you agree that's just their way of phrasing what we already agreed on? They tend to use the term it contains 0 rather than it's got negative and positive numbers in it, but it's still the same sentence. Oh, we need salt. That's interesting. Did they? Am I going to make that? Yeah, they've introduced a fella called unpooled standard error. Did you see that term? Unpooled standard error is actually just standard error. So hopefully it's in that table somewhere. No, darn it. Okay, to get the standard error, aren't we going to have to do our calculation? Sigma 1 squared over n1 plus sigma 2 squared over n2 and stick a big square root around it. And we ain't got time to do that. But whatever that number is, it goes in here. And then lastly, note that the value for the degrees of freedom from this problem are given as 60, which is quite interesting because if you add these two together and subtract 1, do you notice you only get 63? I did mention that degrees of freedom are n1 plus n2 take away 1. That's the one I use. Some textbooks use n1 add the two together and take away 2. I've seen that one. Software has its own weird formula for calculating degrees of freedom. And in fact, if you go and look at the textbook, they'll show you the formula. It's about half a page thick with all sorts of numbers in it. And we ain't doing that, right? And never would we expect you to do that, right? But since they are using 60, I am going to keep 60. And we are going to use salt to find our magic T guy, okay? So, well, I've got to keep my numbers here. And we want a 95% with degrees of freedom of 60. So for our last question, here goes. Use salt. Okay, in the right place. Shrink it up a little bit. Choose T distribution. Put in whatever degrees of freedom they say it is. So I'm picking at 60. Which one of these 4 dots do you pick to get the multiplier T star?
Between.
Okay, and then don't we go here and make it, I think it was 95. And our guy is going to be that fella. And I think I've just killed, oh, I haven't, good. I have no idea where our question. Oh, here we are. So, boom.
We're on 7. I think.
I'm on 7. Right, the number I can't type in because I didn't copy it is 2.0003. How many decimal places to the one? Oh, of course, they only want to 2.00 then. Do you see that WebAssign just kind of does things its own way? I wish I had control over the questions more than I do. But if you figured out what we did in that one, would you agree that question 8 asks us for statistic, standard error, and multiplier? Is that a little bit more consistent? Right.
But it asks
Statistic.
the multiplier on that other question when it's asking for the multiplier.
The multiplier is the name we give to that T star guy. See the one I just found a
Okay.
few moments ago? He's called the multiplier.
So
Right.
to find the multiplier for that, you would do the what is it?
You'd go into solve.
That goes
Yeah.
over. It's that middle one, right? The middle.
To get the multiplier, what you need to do is you need to use salt.
Okay.
And so in this question here, I'm not quite sure. What are you looking at right now? I'm not sure where I am. Are you
So,
saying
We're
salt?
looking at salt right now, yeah.
Okay, right. So if you were doing a question like the one they just did, and you wanted to find the multiplier, the guy that's called T star, somewhere in that story there would be a degrees of freedom. Let's pretend it's 45.
Okay.
You'd make sure it was between, and if you wanted the multiplier for 90%, you would make that guy 90, in which case this number here would be your answer. If you wanted a 95, you would make it 95, and your multiplier changes to that number. And I guess if they did 99, which is the third most likely,
Okay.
that number.
I
would be-
saw that and I was like, what?
Okay, are we comfortable about the multiplier question? Which you have to go to solve. Whew. I'm not good at Russian, but we did kind of get there. So I will see you all on Friday. So make sure you say your last name and bye-bye. And I will hang about for any questions that you have.
Thank you.
Thank
You're
you.
welcome. Bye-bye, guys.
Bye, thank you.
Bye-bye. Right, have you, oh, nobody got a question.